Hello. Today we have here Roman Nagy, who is a postdoc working in the Comenius University in Bratislava, Slovakia. He finished the PhD in 2015 in the same university and now is a postdoc there, and is visiting the institute for 3 months as an Erasmus Plus to work with our group in galactic research, in the Milky Way research. His fields of research are mainly galactic dynamics and also dynamics of the solar system. Thank you.
Thank you, Martin, for the introduction. As I was said, I'm from Comenius University in Bratislava. So I'd like to, first of all, I'd like to show you the brief outline of the presentation. I will be talking about three quite different topics. The first of all, I'd like to introduce my alma mater a little bit to you and tell you something about the astronomy at our university. The second part of the presentation will be about radial migration of stars in the galaxy. Is the research we've been working on at my home institution for last couple of months, a year about. And the last part of the presentation will be about research we've been conducting here together with Martin and his team. It's on the GAIA data analysis, and the last part of the presentation will be just a brief summary. So, Comenius University in Bratislava, it's just some facts about it. This is the oldest university in Slovakia. It's the largest one. We are now celebrating the 100 years after it was established in 1919. It covers wide range of research and education courses. It's got 13 faculties and approximately 27,000 students each year. So this is the main building of our university in Bratislava, and in this building reside Faculty of Law and Faculty of Arts, for instance. So I'm from the Faculty of Mathematics, Physics and Informatics, and where the astronomy is the part of this faculty. So we've got 4 main fields of research of interest at our university. So we focus on interplanetary matter. It's the main topic of our astronomy department. Also meteor astronomy, galactic astrophysics, and space debris research. So I'll talk about it a little bit more. So interplanetary matter is, the research of interplanetary matter is focused primarily on astrometry and photometry of asteroids and comets using our 60 centimeter telescope, which is part of our university observatory near Bratislava. We also focus on the dynamics and physical properties of asteroids. From this observation, we'd like to get some information about rotation rates, etc. But we also conduct a theoretical research on the non-gravitational effects. Non-gravitational effects in the solar system, it contains the action of Poynting-Roberts effect or solar wind and pressure of electromagnetic radiation. So it influences mostly small particles of the solar system, for instance, zodiacal clouds and dust grains in the solar system. So this is the theoretical part of our research activities in interplanetary matter. So the second part of the second field our department is focusing on is meteor astronomy. We conduct observation in 3 different ways: video observations, radar observation, and spectroscopic observations. Video and spectroscopic observations, we combine these observations to get more information about meteors. So I'll talk about it a little bit more because we've developed our own all-sky meteor orbit system, which is the system which it consists of fisheye all-sky camera, and it records meteors during the whole night. It was first of these AMOS cameras was built in 2009, and currently we are operating 11 stations. 5 of them are in Slovakia, 2 of them are here in Canary Islands at Teide Observatory and Roque de los Muchachos Observatory in La Palma. 2 are in Chile and 2 are in Hawaii, Mauna Kea and Halaka observatories. So this is just the location of our AMOS cameras all around the globe. Currently, we're finishing preparation of the new 2 stations will be located in Australia near Perth, and the next expansion should be in South Africa, probably Namibia. So just a couple of pictures of our system. This one is installed here at Teide Observatory. So this is the main camera. All sky camera is located inside because its daylight should damage it. So it's closed now, and this is the spectral camera. For instance, this is the camera installed in Hawaii. And that's just an example how the observations look like. This is the observation from La Palma from January, I think, and it's just the combination from the whole night of observation. So we can see all meteors recorded during these observations, and together with spectral analysis, we can get some more information. So we use this observation to calculate the trajectory of the original meteorite which enters the atmosphere, and this trajectory in space can be used to simulate and find the potential parental body of this meteor. And together with spectral analysis, we can say something about the chemical composition of the parental body as well. So that was just about interplanetary matter we focus on in our department, but there are two other parts or 2 other topics we also concentrate on. The first of them is galactic astrophysics. We primarily focus on kinematics and dynamics of our Milky Way galaxy. We also work on the estimation of effects of galactic slabs on the solar system, especially opaque Oort cloud of comets. And a couple of us are working on the theory of gravity as well. So it is theoretical research, but it's not my research interest. And the last but not least is the space debris topic. So we conduct astrometric and photometric observations of space debris orbiting around the Earth. Especially harm objects are in our interest, so it's high area to mass ratio objects. And for this purpose, we use 70 centimeters telescope, which is also located at our university's observatory. That's the telescope. So that was just brief introduction of my home institute. So now I'd like to talk about research we've been working on for the last couple of months. It's about radial migration of stars in the galaxy. It's numerical point of view. So we know that there are some indications that stars migrate significantly in the galaxy. There are some hints from the chemical compositions, dispersion of radial velocities, and so on. So there are strong hints that stars should migrate in the galaxy. So we try to investigate this effect, and we adopted 2 different approaches. First is standard approach, including dark matter halo. We use Navarro-Frank-White profile to describe galactic dark matter halo, but we also try to investigate the effect of modification of the Newtonian gravity. So how it influences and how it changes changes the radial migration, the amount of radial migration of stars in the galactic disk. We know that the standard approach has many positive sides. It's very good. There is a very good theoretical description of the phenomenon. It's well established, but the problem is that we haven't discovered and we haven't found the particle of the dark matter. So there are some doubts. So we'd like to investigate also the alternative approach. So we focus also on this modification of Newtonian gravity. I won't tell you which of these approaches is correct one. I won't judge anything. So I just try to compare these two results in these two approaches in the context of radial migration of stars. So let me tell you something about this alternative approach. So it's modification of Newtonian gravity. It can be easily described by that we've got two regimes of gravity. The strong gravitational field, it's just ordinary situation where the physical laws should behave in the same way that we experience, for instance, right now. So the strong gravitational fields in the solar system or in the galaxy or near the planets, gravitation should be expressing itself as expected. But the change is in weak gravitational fields, where the gravity should behave in different way, and that's the region, for instance, remote parts of galaxies, or for instance, in the solar system, it's OPIC or cloud of comets, where the gravitational accelerations are low. They are below the boundary between these two regimes is about 10 minus 10 meters per square second. So this is the level which divided the gravity into these two regimes. And when the gravitational attraction or gravitational acceleration is below this value, we have to take into account different laws of gravitational attraction. So it could be described in many different ways, this modification of gravity. So I won't show you many of these functions, but the most I'd like to point out that the observed gravitational attraction or acceleration is proportional to the Newtonian gravitational attraction, which belongs to the just ordinary baryonic matter. So the matter which is visible, we can see, and it should it generates some gravitational attraction and some gravitational acceleration, and this is the one without dark matter. And there is the function which depends on A and A0, and A0 is that value which divides strong and weak gravitational fields. So it's in these theories it should be some kind of new fundamental constant, but it's not important in this talk. So just to demonstrate some positive sides of this modification, for instance, it can really can fit rotation curves quite well. We can see some fits of the rotation curves by these modifications. It also doesn't require any kind of dark matter, so it's the positive side. But also there are some negatives. We need some fundamental changes. So, for instance, general relativity is not compatible with Mond theories. There are some people who working on the relativistic formulation of these modifications, but still it's an open question. Also, there are some cosmological problems. So both approaches have some positives and some negatives. So I won't judge which one is the correct one. So what we are doing in this work is we are inspired by the paper McGaugh Lelli 2016, who investigated 153 galaxies from Sparks database, and they found this interesting behavior of accelerations in these galaxies. X-axis represents gravitational attraction, gravitational acceleration of baryonic visible matter, and y-axis represents the observed gravitational accelerations. So we can see there is some interesting dependence, and I don't know, I won't say that this dependence is due to the dark matter or the modification of gravity. I don't know. So I will consider these observations and these analyses as observational fact. The fact is also that the fit of the data looks precisely like the prediction of this modification of Mond theories. So it is in accordance with these modifications, but we don't know if this fit is due to new physics or just the dark matter behaves in this specific way. And this is the constant I mentioned before, which should be some kind of new fundamental constant of physics in this alternative approach. So what we like to do is to investigate the radial migration of stars in the galactic disk and compare the results of these two approaches. So let me tell you something about the simulation. We take into account the action of the galactic disk, galactic bar, and spiral structure. We investigated the evolution of trajectory of 100,000 test particles, which were randomly distributed, initially randomly distributed in the galactic disk. We just used a two-dimensional disk because of the computational power, which is required for three-dimensional simulation. We're using two different equations of motions to integrate the trajectories of these test particles, and this left-hand side equation of motion belongs to the standard approach with dark matter when we see the gravitational potential of each part of the galaxy, including galactic halo. And the second equation of motion is for the alternative approach with modification of gravity, and we can see that we have to take into account just gravitational potential of disks, spiral structure, and galactic bar. There is no need for galactic halo in this equation of motion. We used, as I mentioned, we used a two-dimensional exponential disk to describe the gravitational potential of the disk. We use a never-frank white dark matter halo profile to describe and to describe the galactic halo. Spiral structure is adopted from Underhat 2011, and we also created our own model of the galactic bar, of the potential of the galactic bar. For instance, there are gravitational potentials of these structures. Spiral structure looks like this, and galactic bar is in this way. So let me focus on the results of the integration. First of all, I'd like to show you just the rotation curves from these two different approaches. There is a curve which should belong, it's analytical expression of the rotation curve from the considering dark matter halo, and this curve represents the rotation curve of the Mond or modification of gravity, non-Newtonian gravity theory. But we can see that the error bars of the simulation are quite high, so both curves can be fit in the same error bars. So this is not the most important result, but I'd like to show you the results of the radial migration of stars. Let me just explain you these plots in the first place. So x-axis represents initial galactocentric distance of the star. So we can see that the star starts its evolution, for instance, here at 8.7 kiloparsec from the sun. And y-axis represents the maximum distance, the maximal change of the galactocentric distance of the particle during the whole integration time. So some test particles migrate really significantly, and we can see that the maximal change of the galactocentric distance is up to 5 or 6 kiloparsecs for some of the test particles. It's absolute value. So that's positive is farther away, and we can see minus it represents it's got closer to the galactic center. Yeah. First, the left-hand side, 2 panels is for Newtonian gravity, and the right-hand side panels represents the effect of modification of gravity. The first plot is for the lowest value of the strength of the galactic spiral structure. So it means that we consider the weakest spiral structure in this case. And the second plot represents the same situation, but with the strongest spiral structure. So the strongest, the highest value of the spiral structure strength considered. In both cases, the spiral structure rotates 0.9 times the rotation of the sun in the galactic disk. So the units of the rotation of the spiral structure, angular speed of the spiral structure, is in the units of the angular speed of the sun. So 0.9 is, I think, the lowest value. No, it's not the lowest value. So we can see the difference, how the spiral structure strength, so the weakness or the strength of the spiral structure influences the radial migration, and we can see that that's just what was expected, that stronger spiral structure can generate more significant radial migration in this case. The effect is more visible in the regime of modification of Newtonian dynamics, and there the migration is even higher, more significant. So the similar comparison is in this plot. We can see upper and lower panel. Upper panel represents the Newtonian gravity, and lower panel represents the modification. And now we compare the rotation, angular speed, the changes of the rotation of the spiral structure, how it influences the migration. And we can see also that the effect of the changes of the rotation of the spiral structure influences the migration significantly. We can see that for 1.1 rotation of the spiral structure generate the strongest, the more significant radial migration. Again, the effect is more visible in the regime of modification of gravity. The last comparison, before I come to the time evolution, is the effect of the galactic bar. The left, both plots are for the Newtonian gravity. The left panel is the result of the whole galaxy, including spiral structure. So it's one of the plots we've seen before. And the right-hand side panel is just for the action of the galactic bar when the spiral structure is not taken into account. And we can see that the radial migration is significantly decreased, and much less particles migrate significantly when just a galactic bar is the disturber in the galactic disk. So just action of this galactic bar cannot generate significant radial migration statistically. So now let me show you the last two slides from this part of the presentation, and this is the time evolution of migration of stars. Once again, upper panel represents the Newtonian gravity, and lower panels represents the modification of gravity, and we can see how the migration behaves during the integration time. This is for time range till 1.25 gigayears, and we see that from these pictures and from the deeper analysis that when we consider modification of gravity, the process of spreading of the stars through the disk is more significant, it's much faster. So this modification of gravity increases the speed of the transport of mixing of the galactic disk. And we can see this in different time range from 1 gigayear to 5 gigayears. And we can see that there are also gaps and denser parts in these plots, and this should be the cause of the resonances in the galaxy. And there are also plotted some lines which represent the resonances. The blue lines are resonances with the spiral structure. We can see these blue lines are the resonances with the spiral structure, and the green lines are for the galactic bar. Solid line is co-rotation resonance, so this one and this one. And the dashed dotted line is Lindblad 2-to-1 resonance, and dashed lines are for Lindblad 4-to-1 resonances. So it's just to see the effect of the resonances is the most important in both regimes, but it's just it's not the point of this comparison. So we're finishing this work currently. So unfortunately, I cannot show you more beautiful pictures and figures. So we finishing this work. We'll be finishing this work in a couple of weeks. So, yeah. No, we follow the distribution of matter in the disk. So the initial position of stars follows this distribution as exponential decrease of number of stars. Yeah, exactly. Okay, so let me show you some results of the preliminary results of the research we've been working on during my Erasmus Plus stay here at ISC with Martin and his team. So we'd like to investigate and analyze data from the GAIA data release 2, and we are looking for the flare. Is a flare or present in the far region of the galaxy? That's the question how to start this part. So what is the galactic flare? It's the increase of the scale height hz of the disk with increasing galactocentric distances. So we can see this is hz in the disk, which can be described with exponential decrease of the density. So it means that the galactic disk becomes thicker and thicker when we go to higher galactocentric distances, so in the remote regions of the galaxy. The problem is that these regions beyond 15 kiloparsecs, for instance, are difficult to analyze because of lack of the data we've got there. So we used GAIA data. We'd like to use the GAIA data to investigate these remote regions of the galaxy and look for the take a look for the potentially galactic flare there. So the problem is not a problem to get the information about the gas. So we can find some results in the literature about the HZ and the galactic flare derived from the distribution of the gas in this remote part of the galaxy, but for stellar disk it's a little bit more tricky. So GAIA data release 2, it's published, it's available publicly from April 2018, and it contains less than 1.7 billion sources, as you all probably know. But for our purpose, we need all 6-dimensional information. We need all positions, and we need all components of velocity. So we've got just 7 million sources, also with radial velocities. Okay. So we need these 7 million sources to investigate these, to take into account during our analysis. This is the an example of analysis done by the team. This is the paper which was published just after the data release was made public. So we can see the results of the analysis, and let me explain to you. We've got on axis the galactocentric distance from 4 to about 12.5 kiloparsecs. The y-axis in this plot represents z direction, so it's vertical direction, and we can see the slice of the disk, and the color coding is for the z component of the velocity, and the right-hand side panel is the same, just plotted is the sigma of this z component of the velocity, so dispersion of velocities coded in colors. So this is the result of the paper which was published just right after the data release, and we can see that we cannot go, get to higher galactocentric distances. We are restricted to about 13 kiloparsecs from the galactic center. So we cannot use this analysis and this data directly to find a flare in these remote regions of the galaxy. So, but there are two different ways to analyze the flare. So the first is velocity dispersion. We can use these data of sigma Vz. So this dispersion of z direction and dispersion of velocity can be used to find a flare in a remote part of the galaxy. But we need the data there. So we can use this extended kinematical maps, which was published and was made by Martín and collaborator in this year, which provides 3-dimensional velocity maps for extended range of the galactocentric distances. Using some statistical approach is the statistical deconvolution of the parallax error based on the Lucy method. And using this statistical approach, we can get to higher galactocentric distances up to about 20 kiloparsecs. And this is the example of these 3-dimensional kinematical maps we can see that we can get to even higher galactocentric distances, to 20 or 22 kiloparsecs from the center. And this analysis and this data, these maps, can be used to find a flaring also from this dispersion of the velocities. We can see the same type of plots that we've seen before. The left panel represents this is the z component of the velocity, and the right-hand side panel represents the dispersion. The center panel is for errors, and this analysis can also lead to the discovery of the flare, and we can see that this result shows us hz, so it is scale height of the disk, and it's increasing, the value of hz increasing with increasing galactocentric distance. But for now, we get to 12 kiloparsecs in this analysis, particular analysis. So, but there is another way to find to try to discover a flare, and we can take a look on the directly on hz, how it changes in the galactic disk. So we can take a look on the distribution of matter and the density of the disk, and we can calculate the hz for different galactocentric distance. So for instance, Tavakoli 2012 calculated the changes of scale height of the gas, atomic hydrogen gas in the Milky Way, so they could get to higher galactocentric distances, but this is just the case of the gas, and it's not the case of the stellar disk of the Milky Way. López-Corredoira and McGaugh 2014 used stellar data from SDSS survey, and they also calculated the changes of scale height for thick and thin disk in higher galactocentric distances. We can see that they could get to even to the 30 kiloparsecs, but the increase of the hz in this remote region of the galaxy is quite visible, despite we've got relatively high error bars there. For instance, Carbella et al. 2014, they analyzed stellar data of thin disks, and these markers, red, blue, and black, represents the values of the thin disk, hz of the thin disk for different galactic longitude. But we can see that even in this case, they couldn't get beyond about 15 kiloparsecs. So we cannot say if there is a flare in the stellar disk and how strong it is. So that's just the result of the simulation. Ma et al. 2017 presented, and these black crosses represents the hz for thin disk, and these plus markers represent the changes of the hz for thick disk. We can see that hz for thin disk is relatively close to the hz, so scale height of very young stars, so it's in accordance with our understanding of thin and thick disk of the galaxy. And the last result from this overview, we can see the result from Lee et al. 2019. They already used GAIA data from DR2 in this work, and they tried to find the galactic flare. They could get to about 15 kiloparsecs. They focused only on OB stars, so it means that they focus on the thin disk, and we can see the changes of the hz with the galactocentric distances still about 15 kiloparsecs. But what we want to do, we want to extend this range till about 20 kiloparsecs to analyze it. So we use the whole data set, and we need for this purpose the density maps with extended range of galactocentric distances. So we need to use Lucy method, which is can statistically extend the range we can get, and we can have these density maps for extended range of galactocentric distances, and we can see that we can get to about 20 kiloparsecs, and this plot is from -3 to 3 in vertical dimension of the disk, and the color coding is for the densities. And analyzing these extended density maps, we can find flare in these remote regions of the galaxy, and this is our preliminary result. We can see in these yellow markers represent HZ, so galactic scale for the thin disk, and green is the fit of the data, and we clearly see the increase of this HZ of galactic scale height even in remote region of the galaxy, about 16, 17 kiloparsecs. And we separated it by considering, we fitted two exponentials from our data. So we used the data till 3 kiloparsecs, 3.5 kiloparsecs, and we fitted the densities by two exponentials. One is for the thick and one is for the thin disk. But also we tried to find, we fitted also only just thin disk for about maximum distance 1 kiloparsecs, and we also compared these results. But these results from both approaches are in accordance with one of each other. So, and blue markers represent the thick disk, and the red line is just the fit of the data. And we can clearly see that the values of HZ are really high in this region, in far region of the galaxy, and we'll see if we can get even to even higher galactocentric distances during last stage of this analysis. Okay, so let me just sum up the presentation. So we have investigated the radial migration of stars in the galaxy using three approaches: standard approach with dark matter and with modification of the gravity. The second part of the presentation was dedicated to research we've been working on here at IRC, so the analysis of GAIA data, and we have focused our attention on the possibility of the galactic flare, so the flaring of the disk and thickening of the disk in the remote regions of the galaxy. Okay, thank you very much.
You, Roman. Okay, so we have some time for questions.
Very interesting, and I think definitely going much farther away would give a lot of clue on the nature of the SIG and the SIG disk for this for the Milky Way and in general. No? So I have multiple questions. I will try to make only two. So the first one is that so apparently, if you go farther and farther away, the transition between SIG and SIG disk disappears, and somehow the SIG disk becomes the SIG disk because the scale heights becoming to approach, and at some point, if you say let's go to 20, 25 kiloparsec, there's only like a SIG disk component, or everything could be consistent with that because the two scale heights are compatible. So at some point, they're basically the same structure, no? Because you cannot distinguish fit into exponential two things that are having the same scale height. No? So I would like to know your opinion about that. And the second one is, do you think the flare can be explained with the Mond theory? Because you would expect that so the larger the flare, I would expect the worse for the Mond, right?
Thanks for the questions. First question, yes, but we didn't reach these extremely far regions where this might become just one single disk. But in this data about 16, 17, and 18 kiloparsecs, there is still both disks could be distinguished apparently. It's not, we don't know how stellar disk behaves after the 20 kiloparsecs. So it's just, at least I don't know it. So we'll see if we can, what the highest galactocentric distance we can get to, and analyze data there. And then I can say something about this, but for now I don't know the behavior of thin and thin disk, and is potentially becoming one disk in this far region of the galaxy. Because we can take a look. We can see the results of the hydrogen gas, but it's different component of the disk. So it doesn't mean that the stellar disk behaves in the same way that gases do. And the second question, it's really interesting how to connect the flare with the Mond theory. I have one slide to demonstrate it. Sanchez and Salcado at 2007, they tried to fit their data of the flare by different versions, different functions of modification of gravity, and I don't have them here, but they tried two different functions, Mond theory, and tried to fit their data for hydrogen gas, and we can see that there are these two fits are for different values of H0. That's the value, that's the fundamental constant in Mond theories, and we see that none of them can fit the data for the gas. So I don't know if it is different in a stellar disk, but I doubt so. But it is very interesting way how to exclude or at least be suspicious about the theory.
Mond will argue that this is a very simple explanation, and then you have all the kind of satellites falling and injecting energy and so forth. So don't worry, you would never rule out Mond.
Yes, I wonder about your numerical simulations in which you show the effect of the bar and the spiral waves. You observe gaps and overdensities. I want to ask you what are your initial conditions in terms of velocities? The initial velocities, if they follow a distribution or a stationary state, let's say.
Yeah, we considered in this particular plots that the initial radial velocities are 0, but we also run this integration with distribution of initial radial velocity, and it didn't change much about the results. So we couldn't see the result comparing these plots, but we tried both approaches.
That particles that let's say starts weighted by the initial distributions, because maybe, as you know, the paper of Denen et al. In 2000 used that approach of propagation, so you can weight the contribution of each initial condition in at the end of the evolution, just to weight the contribution of each gap of each over density.
Hi. About this first part of your presentation, have you compared with the observations? So you have different predictions of Mond and Newtonian, and is there any comparison with observations?
Short answer.
So who is more favored? Which is the model which is more favored by the observations?
Yeah, we tried to compare compare it in a simple way, but we haven't compared it in just in the difficult, in some complex way. But the results of the simulation on these integrations, the difference is not so significant to be potentially visible in the observation data. That's our preliminary result of this comparison with the observation. So we cannot distinguish both regimes or both approaches from the data. But that's just first stage of the analysis. Yeah, low, yeah.
I also wanted to talk about this plot. I recall a paper from 2009, Skundrich and Bini, where they also study radial migration, and they have a series of papers, I think, and they say that transient spirals have a big role in this radial migration thing. Now, this doesn't have transient spirals because it's a fixed potentials and test particles. So I assume that the goal here is to distinguish between the two Mondian and the dark matter possibilities. But do you know if transient spirals would, having a self-consistent simulation that would include transient spirals would imply a big change into these simulations or not?
I don't know for now, but I know about the paper you mentioned. So there are many papers investigating radial migration in different ways, and also hydrodynamic simulations and so on. But the results are surprisingly contradictory a couple of times. So it's difficult to say if some particle effect could significantly change significantly change the amount of the migrating stars. But from my point of view and my previous works, I recollect that for instance, the spiral arms are the most important and the most important cause of this migration.
So the grand design ones, the permanent ones.
Yeah, not just permanent, but also transient.
Transient, yes. I was wondering what's the biggest effect, if it's the transient ones or the ones that have a fixed potential, like here.
But I don't know. I cannot answer this question.
Coming back to this experiment, don't you think it would be interesting to explore this migration at the very outer part of the galaxy, so you can have clear signatures that you can compare with the data, no? Because there, as we have said, is where you expect the maximum difference between the two models.
Yeah. That's I don't have these plots for far region of the galaxy, but we have the results for them. But the problem is that we have relatively low number of the test particles. It's 100,000 particles. It's not enough to cover these subtle changes in the far region. So we don't have enough particles in this region from our simulation. But this is the reason. This is the cause of the low number of these particles there. So, but it's one of the way how to see is there any difference between the prediction of both theories.
Any final comments, question? One question, anyone? Okay, so let's thank the speaker again for an interesting talk. Thank you.